Okay. I guess the mic is on, so I guess we've started. So first of all, thank you for the opportunity to speak here at SciPy in Japan, the inaugural year, the very first year of this conference. So as I was preparing for this, one of the things that I was not sure about is what would be the level and the familiarity with Chainer of you. So I'd like to start with some questions. How many people have heard of Chainer before? Okay, that's a good number of people. Okay. How many people have used Chainer before? Still, okay. Great. How many people have committed to Chainer on GitHub? Excellent. Okay, that's great. We have room for growth there. The other thing I was wondering about is how many people, for how many people is English your native, your best language? Okay, and Japanese? Okay, so mostly Japanese speakers with a good number of English speakers. I'm a little, I'll start Japanese style and apologize. Chainer is written here in Japan by a Japanese company of which I am a foreign employee. And we thought that this conference would be more Western and have more English speakers, so I'm speaking to you today. I do speak Japanese, but maybe not as technical Japanese, so my presentation will be in English. So for those of you who have come here not having heard about Chainer before, which there are a few of, I hope you'll understand it. There are other frameworks out there, and we think Chainer is one of the best, so I hope you'll appreciate some of the benefits that Chainer brings. For those of you who have heard of Chainer before but not used it, I hope you'll see some of the ways that it can be used and some of the advantages that it can give you other platforms. And for those of you who have already used Chainer, I'll be talking about some of the next steps of Chainer. So where we plan to go to from here and how we're going to continue to innovate in Chainer to make sure that it's the best framework for researchers. So my name is Crissman Loomis. I work for Preferred Networks, which is the company that originally developed Chainer, the open source framework Chainer. We're actually just down the road from here, about a 12-minute walk from my office. So it's great to have all of you here in Japan. So the platform that I'll be talking about is the deep learning framework of Chainer. And our goal for it really is to make it the best platform for doing iterative research on and development. So the distinction of Chainer originally had when it was created. At the time, there was Theano and a few other frameworks that existed, is starting with the define by run. So this is making it so that when the neural network is created, when you code it, it is actually executed and formulated when it's run as opposed to pre-compiled. So the other frameworks would set up the connections between all of the neural nodes, and it would be in a fixed compiled framework. And then when you run, it would give you, well, let's talk about some of the benefits of that. So Chainer was the very first framework to use the define by run system. Then that was copied by PyTorch. It's open source, so copying is part of the accepted approach. And PyTorch has done quite well with it. And then after that, MXNet came out, and they also wanted to use more of a define by run flexible approach, so they put Gluon on top of it, which made it more dynamic. And as of version 2.0 for TensorFlow, also define by run is the default version. So define by run in TensorFlow is called eager mode, by the way, which is another way of basically calling the same thing. So what define by run gives you is that the neural network, when you're writing a neural network, it's actually defined just in straight Python code. There's nothing behind it that is unaccessible to you, and the error messages that come up can be directly interpreted and are defined at the runtime. So it can be written as plain Python script, and the variables hold how they are computed, and they hold the information in fields inside of them, how they're computed, so the gradient is automatically computed from that. So this gives you the model description is done, all within Python code, and the distributed training as well. All of that is straightforward and can be explored throughout the Python, and as well as serialization for export and import of codes and models that you have done. So everything is optimized for the defined by run style programming. So that gives you plain customizable Python code that you can just read as you're going through it, fetch the next any batch, concatenate it, transfer device, forward propagate, backward propagate, update the parameters, compute the gradients, clean up the gradients. So the other thing that Chainer is highly customized for is for running on GPUs, which in modern calculation is pretty much required if you're doing large amounts of data processing. So for doing calculations on the GPU, Chainer uses CuPy. In the first versions of Chainer, CuPy was part of Chainer. It was something that we worked through, and we realized we needed to do calculations on the GPU, so we actually included that within the code itself. But around version 3 of Chainer, we realized that there were many other uses also for having NumPy syntax that would do calculations on the GPU for speed. So if you've used other frameworks, you might have had issues or noticed problems if you use a lot of NumPy, where you found that the commands that you were used to using in NumPy that you've used a lot were slightly different. Instead of axes, you have dimensions or other things that there's some slip that would slow you down when you're trying to do coding. So from the start, we made CuPy to be basically exactly like NumPy, but do the calculation on the GPU. So it can act basically as a drop-in replacement. And I believe later this afternoon there's a presentation that's all about CuPy, so I'll mention it in passing here. So you can basically, instead of importing NumPy as NP, import CuPy as NP or CuPy if you're willing to do the search and replace. And you can also, using CuPy functions as NumPy, to move from the GPU, data on the GPU over to the CPU, and then back again using the asArray to move data that's currently on the CPU over to do calculations on the GPU. And this is just to show you that the code basically doesn't change and can be mixed and matched. CuPy has large coverage of the NumPy functions. It does not cover all of the functions at this point. Pretty much all the functions you would use for deep learning are covered. But you can also, if you need to fall back to a NumPy function which isn't covered, it's available on the CPU as always. So CuPy, the strongest part of CuPy is on NVIDIA chips. Although there is an AMD or an OpenCL version of CuPy available as well that's made by another group of people. But it's strongest on the NVIDIA chips because of the infrastructure and the coding that NVIDIA provides with us for convolutions, pooling, LSTM. You can also write your own custom kernels within CuPy. So if you've done work with multiple functions, you might know that you use a lot of time as you go to Python between the functions. And if you can put multiple functions into one kernel that is then run at one time, it gives significant speed benefits. And CuPy provides access to that, both in a Python format, and also you can actually write direct C code in there as well if you wish. And it also provides FP16 support for floating point, 16-bit floating point, which I'll be talking a bit more about later. So mixed precision training is a drive across the industry, really. It offers significant benefits in speed, up to 4 times as fast when you're doing your calculations and training. But the floating point FP16 can't be used for everything. For the activation functions or some of those things, it's fine, but when you're accumulating gradients, you need to have greater definition. So at that point, you're going to need FP16. Tensor core support's available, and in Chainer, we have techniques for mixed precision training, optimizer, set loss scale, or use FP32 for the update to make sure that your gradients are accumulated in FP32. And currently, we're working on mixed mode, which would automatically then, for activation functions and calculations which don't require floating point 32, will allow you to go to floating point 16. And then for the other actions which do require it, will then automatically change it, broadcast it out to 16 or to 32. So, what are the things that are really required, even now, for deep learning frameworks? One of the things that always comes up is speed. It's all about trying to get the results out faster, to be able to iterate faster, to see where your model worked or didn't work. Another thing is environment support. It's not enough just to train your models on your clusters or on your computer. You need to be able to support different environments, perhaps for the deployment of your model, to deal with robotics or other things, or actually have computing on the edge. And the other thing is quick deployment, so application of research outcomes, so that you're able to move it to a faster environment. So as of the Chainer version 6, which we are currently in release candidate 1 for, and we'll be releasing next month, we're introducing Chainer X. So the idea behind Chainer X is that we want to continue with the NumPy-like text and syntax for it, using ND-array and autograd. And but we're writing Chainer X in C++ as a backend. So while the front end will continue to be the Python that you can use quickly and adaptively, very understandable, interpretable, it has a thin binding layer and then C++, which allows us to speed up significantly. As we were looking at the bottlenecks and where the limitations to speed were, for about the past, since Chainer was created, the bottleneck has always been the GPU. So we always told NVIDIA they need to make it faster because our code could run faster if their GPU would just do the job. But we're getting to the point where Python is now, the Python work that's done on the CPU is going to start to be the limiting factor. And so in advance of this, we started working on Chainer X and moving the back end of Chainer itself so that it's C++. So this will also give us ability to access the broader access of C++ with pluggable device backends, so that other infrastructures other than NVIDIA chips or normal GPUs can be used. We're hoping that this will be interesting to people and that there will be customizations of Chainer X to use on other structures. And also with the pure C++ API, it can be run then without having the Python overhead for some devices that don't necessarily support Python or do support it, but you want it to perform at a faster speed. So this is increasing the speed, environment support, and also allowing for quick deployment for Python-free native applications. So you can see the stack gives you multiple layers that you can interact with Chainer X at. So if you're looking for the flexibility that you've seen with Chainer itself, we have a high-level API, which is just through the standard Chainer interface. Existing Chainer code should largely be deployable. We're not at the final release yet, but just deployable as is, and then just experience the speed up of having Chainer X on the back end. We'll also have a Chainer X Python API where you can port code with less overhead. And then you can also interact directly with Chainer X with the C++ API. And then this can then go directly back to the CUDA backend, which is going to be a strong option. But also it has availability as just C++ code. It could be put on a custom backend or native backend as well. So, of course, one of the big things is the time tests. So this is a heavy iteration testing that we did. Just straight Chainer using NumPy was about 15 seconds per iteration. When we used Chainer X, this is just on the CPU, it was about half that time, about 8 seconds or so. And then when we used straight Chainer X through the API, it was about 2 seconds, and that was actually faster than PyTorch. It's kind of an artificial example to show what will happen as the CPU becomes the bandwidth, but this shows at least that we're on the right course and making sure this isn't the limiting factor. So the roadmap for Chainer X, we're currently right now in getting ready to release version 6 next month. It has basic operations and integration into Chainer. Version 7 will be released in November of this year with a wider coverage of operations. We think it should be ready for most users at that point, and the C++ API will be more accessible. And then going towards the future, we'll be looking to make it easier to deploy, get some more backends and other ways that we could work with it, and have a wider coverage of already compiled models. So the Chainer itself works mostly on the training side of things, and we also want to cover the entire life cycle of neural network models. So we also have put a significant amount of time into working on a Chainer compiler. So Chainer supports Onyx, the ONNX format. And we have programs that will do that conversion for you into ONNX. And then from ONNX, it can be then compiled into a ChainerX virtual machine, vendor-specific graphic formats or native binary. And it can be executed then with ChainerX as a C++ program. We use ChainerX in our own company for most of our work. We're an industrial artificial deep learning company. And so we've covered the use of neural networks across a wide range of areas. And we've developed specific modules then to make it easier to work in those specific areas. We have Chainer CV for computer vision tasks, classifications, object detections, semantic and instance segmentation. We recently computed in the Google Open Images Challenge, which was hosted on Kaggle, and our PF-DET took second place globally for bounding boxes, multiple bounding boxes per picture. It also has a simple unified interface, and we have guaranteed reproduction of some of the classic computer vision models so that you can see that the performance is the same as the original paper. We also provide Chainer reinforcement learning, which covers a wide range of the classic reinforcement learning models, DQNs, double DQNs, PPO, TRPO, actor 3 critic, and other things. And it has a nice clean API and abstraction. You can use multiple design choices, discrete or continuous, recurrent models, asynchronous training, and supports the typical environments that you'd expect, ALE, OpenAI, GIM interface, and other places where you do reinforcement learning. We have a couple of specialized modules. One is for Chainer chemistry. One of the other things that we work on is microRNA for cancer identification. And this then can be used for specific type of chemistry experiments and using models and graphs for chemistry, as well as Chainer UI that then allows for a graphical interface for watching how your training is proceeding and being able to change the training and other things. So that's the basic introduction to Chainer. Thank you very much for listening. We're continuing to work on advancing the Defined by Run API design and make deep learning easier and more accessible. Contribution is always welcome, and I guess I'm open for questions. Thank you very much.
Thank you, Crissman. That was very good. Any questions for Crissman? Anyone? I'd like to. Oh, there's a question there. Yep.
日本語で質問させてください。ありがとうございました。
Oh, you're fine with Japanese.
I'm fine.
Take it back.
Hi.
チェイナー X の紹介をしていただいて、いろいろな性能がすごく高くなるであるとか、とても使いやすいフレームワークだということは理解できたんですけど、これまで書いていたチェイナーのコードをチェイナー X で動かすことができるんでしょうか。もしかしたら説明していただいたかもしれないんですけれど、新しい書き方をしないとチェイナー X での性能は発揮されないんでしょうか。
So I guess I respond in English, right? To make it easy for, okay. It's my interpreter either way. 日本語で答えします。チェイナー X は基本としてはその Python の例を使えばチェイナーのコードは今まで通りで使えるようにコーディングしていますので、もちろん議論あったんですけど、もう今のコードをもうそのままに放っておいて、チェイナー X は別のコードにして、でもうコンパティビリティなしにするかどうか議論して、でやはり皆さんの今まで作っていただいたモデルはこれからも使えるようにしますので、ちょっとそこはもちろんそのフルのチェイナー X の速さはちょっと使えないんですけど、でも今のコードは目標としては今のコードはそのままチェイナー X とも使えるようにしてあげたいと思います。
安心しました。ありがとうございます。
はい。
Any further questions? So I actually have two questions.
Okay.
First one is about you were talking about different backends to CUDA, in particular in my research, and at inference time, it would be really nice to have inference on my laptop. You know, I'm going home and exploring my data set, and I don't have an NVIDIA card, and I think a lot of people have that problem, especially since
all the Macs here, yes.
Yeah, exactly.
Share the same.
So how's that going?
Well, the Chainer X is it's first of all it's designed to speed up the Python, the CPU overhead. So that's going to be much faster, and it doesn't require using the NVIDIA cards. Okay. So it's going to be slower than using a GPU, but it can be done, especially for the inference stage. One of the benefits of it is that it then will speed up the inference stage on the CPU as well. Okay. So it works well. There is OpenCL, and we'd like to have a backend for AMD chips and the other graphic chips, but that's sort of a demand, and also that we need more interaction with AMD to work that out. So
I thought OpenCL did work with AMD as well as integrated graphics. Am I wrong there?
It does, but it doesn't have the same it doesn't have the functionality. I can't speak as much confidence about the OpenCL because that's done by another party, not us, but it is available. We know it's out there for CuPy, actually.
Okay, fantastic.
Okay.
And the other question I had was that there's this sort of new philosophy that speeding up code is not the programmer's job, it's the compiler's job. And so there's all these tools now like Numba that will take Python code and make it as fast or almost as fast. In my case, I've gone to about 30% of C++. So have you guys explored that? And
yeah, we meet with the we meet with the Numba people and we work with them. So Numba is currently converting to use CuPy for their GPU acceleration. Right, so we're all, and we also do sometimes do bench tests where we'll take Chainer code and then run Numba on it to see how much faster, and then there's a speed up that comes from that. Yeah. So yes, definitely we work with them, and we're trying to continually make that faster. And the trouble is that as you know, the backends are becoming more and more specialized, which means that you need something like Chainer X to run on more accelerated backends. Then that will allow you to get the benefit so that your code can stay your code, but it speeds up thanks to the hardware.
Exactly. Yeah. Okay, thank you.
Okay.
Any further questions? Okay, so I think we have a half-hour coffee break, and then we will start back here at 4 o'clock. Please thank Crissman again.